This is the last part of the lecture on concrete. Today I am going to talk about special concretes, concretes that are not conventional. We will look at different types of special concretes and talk briefly about each of them. On this header slide here, I have an interesting building. It is the CNIT building in Paris, built in 1958, which is basically a large shell. It has a huge shell roof. It is a doubly curved ribbed shell, and it is supposed to be the largest unsupported concrete span enclosed space. And here on the top right you see the shell. This is the interior. They have a lot of shops inside and lot of open space, no columns at all. This is one of the supports. You see the ribs at the top, and this is the center of the interior. You see the ribs and you see the inside of the shell. So, it is a very nice structure that has lasted a long time in good conditions. Now, what are special concretes? As I said, special concretes are those that are not conventional, not very widely used, but probably in the future they could be used more and more. This is a list of special concretes: high strength concrete or high performance concrete, self compacting or self consolidating concrete, fiber reinforced concrete, lightweight and foamed concretes, shotcrete, porous or permeable concrete, roller compacted concrete, autoclaved aerated concrete, high density concrete, heat resistant and refractory concrete, underwater concrete, polymer modified concrete, recycled aggregate concrete, geopolymer concrete. Now, some of these we will go into little bit more detail. Starting with high strength or high performance concrete. This is a concrete which satisfies all requirements in terms of all the critical aspects of fabrication and utilization at the lowest possible cost. So, this is something that is not a unique mix, or not, there is no single high performance concrete. Depending on the application, depending on the critical aspects of that particular applications, we have to define what a high performance concrete for that application would be. Generally, high performance goes beyond just strength. It today implies both durability and strength, and it could bring in other parameters which we can use to define performance. In terms of high strength and high performance concrete, where do we use these concretes a lot? In slabs and columns of high rise buildings. This leads to more slender elements, giving more floor space and therefore more income to the owner in terms of rental or sale. The concrete also increases the stiffness because of the higher strength, and this means that there are less deflections or deformations and less material can be used in the construction. Slender elements also are aesthetically more appealing. They look better, and that is an added advantage. In terms of bridge piers and decks, high strength concrete gives more durable structures, and again because of the slenderness the structures are more elegant. In terms of marine structures, because of the higher compactness of the microstructure, we get less permeability and therefore higher durability in the structure. The structure also weighs less because of less volume of material used in its construction. These are some of the applications of high strength and high performance concretes. What are the important characteristics? How do we go about getting a high strength or high performance concrete? First of all, we have to start with good quality material components. The aggregates have to be strong and have to resist failure, because in high strength concrete now failure of the aggregates can occur as opposed to the cracks going along the interfaces that we see in conventional concrete. So, the material components should be good to start with. There should be a dense packing of aggregates, that the aggregates put together should have as little voids as possible among them, between them. This would require less cement paste and the strength would be better in the concrete. The water cement ratio that we use is normally low, generally less than 0.35. This is also an upper limit for durable concretes. Generally, if you want a concrete to last for a very long time, the water cement ratio should be low, and a thumb rule is that it should be less than 0.35. High strength and high performance concretes always incorporate one or more pozzolanic mineral admixtures. This is pozzolanic. No? So, what are some of the important characteristics of high strength of high performance, or what are the important characteristics of high strength or high performance concrete? First of all, we start with good quality material components, that is, the cement should be of a high grade and aggregates should be of good quality. Remember here now, the aggregates in high strength concrete can break. In normal or conventional concretes, we have cracks going along the interfaces between the aggregates and the cement paste. The aggregates themselves do not break. Here aggregates can rupture, and therefore we need to have good quality strong aggregates. Next, there should be a dense packing of aggregates, that is, when the aggregates are put together to form the skeleton of concrete, the voids among them, the voids between them should be as low as possible, so that we require now less cement paste and there is strength coming out the transfer of load between the aggregates from one aggregate to the other. We also have a low water cement ratio, normally less than 0.35. Remember that when we are talking about durable concretes, we always would like to have a low water cement ratio. Similarly for strength, and as a thumb rule, it is good to have water cement ratios less than 0.35. These concretes also incorporate one or more pozzolanic mineral admixtures such as silica fume, fly ash, slag and metakaolin. They could be ternary blends, for example with silica fume, fly ash and cement, which also is beneficial. Because of the low water cement ratio, possibly higher cement contents and the presence of the mineral admixtures, we need a good superplasticizer to give us the workability, otherwise the concrete is too sticky and will not be workable. So, a proper superplasticizer and an adequate dosage is very important to obtain the desired workability. Final characteristic, which is again very important, is that curing is very much necessary in these concretes. Remember, now we have low water cement ratios, we have a high fines content, and if curing is not done properly, this could lead to early cracking due to shrinkage and thermal stresses. As a consequence of these characteristics, the important properties of high strength and high performance concrete are that it has a dense microstructure, that means it has less porosity, fewer defects and strong interfaces. The interface between the aggregate and the cement paste, instead of being a weak link in the composite, now is strong, and therefore failure does not preferentially occur through these interfaces. Also, water and other aggressive chemicals do not find a path through the concrete that easily. Consequently, we have higher strength and low permeability, therefore the durability is much better. One of the disadvantages or one of the peculiar aspects that we have to take into account in design is that higher strength concrete in failure is more brittle than normal concrete. So, that means the reinforcement has to be designed such that we can avoid such brittle failure, and we have to take this into account in the design. This aspect of the brittleness can also be seen in these stress strain curves. Now, if we look at the mechanical behavior, we generally worry about the compressive behavior, and here we have now the stress versus strain in compression. A usual concrete, say a 25 or 30 megapascal strength concrete, would have a curve like this. You have a linear part, a non-linear part, a peak, and then afterwards softening occurring. And at around this point, the non-linearity starts because of the cracks that develop along the interfaces. These cracks now bridge and cause failure ultimately. In high strength concrete, you have a much more longer linear part, obviously because of the better density of the microstructure. We have a higher stiffness. This linear part extends longer. We have a very short non-linear part. We reach the peak, and then there is a very sharp drop in the post peak behavior. This is what gives higher brittleness or reflects the higher brittleness of this concrete. The reason why we have a longer linear part is that when we look at the microstructure of high strength concrete, we have eliminated the interfaces which are weak, and we have eliminated defects. So, therefore, there is very little cracking in the pre-peak region. There are very few cracks as opposed to what we saw in normal concrete. Consequently, we have more pre-peak non-linearity, we have more pre-peak linearity, that is the linear part is longer, there is less pre-peak cracking and no crack coalescence, that is the joining of the cracks and cracking is less visible or occur less in the pre-peak of high strength concrete, and we have this characteristic brittleness reflected by a sharp post peak descent in the stress strain curve. So, this is basically the difference between the mechanical behavior of high strength concrete and a normal conventional concrete. Some examples of applications which are very characteristic, which have utilized well the properties of high strength concrete are shown here. This is 2 Union Square, a building in Seattle built in 1988, 58 stories high, and what was done is the core of this building was made up of 4 3-meter concrete pipes, where you had concrete filled steel pipes, that the steel pipe formed the mold and also part of the reinforcement of the concrete column, and this formed the core of this building. Here 130 megapascal strength was used, and basically because of a very high elastic modulus requirement of 50 gigapascals. This type of structural configuration has extended, and now lot of high rise buildings have this very strong stiff core in the middle and the floors emanating or fixed to this core. In terms of bridges, again we have lot of examples of high strength concrete application. This is the Confederation Bridge in Canada, built in 1997, 13 kilometers long, 59 spans, and it was interesting that this was one of the first structures to have a 100-year service life built into the contract. We talked about this earlier, that this means that lot of aspects related to durability have to be thought of in the design, and one of the reasons that high strength concrete was used is that it is more durable because of the very low permeability. The spans were built with 55 megapascal concrete, all the spans over the ocean, the marine spans were built with 55 megapascal concrete. The bottom of the piers had ice shields that protected the concrete columns from ice impact and expansion. This was built with 100 megapascal concrete, that is these lower parts. Another application of high strength or high performance concrete is in offshore platforms. This is the Hibernia offshore platform, built in 1997, more than 100 meters height, and it is designed to resist iceberg impact. And here a high strength concrete with a lower than normal unit weight was used, 2200 to 2250 kilogram per meter cubed. The elastic modulus was more than 32 gigapascal, and the characteristic compressive strength was 69 megapascal. Slip forming was used in the vertical parts, that is, for example, in the caissons. Here you see the caissons during construction. Vertical slip forming was used, where the formwork moves up slowly. Here it moved up at the rate of 1 meter per day. So the concrete has to set fast enough such that this formwork can move up. So high strength concrete can also be used in slip forming. Now we will go on to another concrete which is catching up, has been around in many countries for a long time. It is called self compacting or self consolidating concrete. It is a concrete that is capable of flowing within a mold or formwork, fills it completely without any segregation, can pass through reinforcement and consolidate under its own weight. Therefore, it is a concrete that does not need any vibration. It can flow and fill up the formwork and not get stuck in the reinforcement. In order to achieve this, we have certain important characteristics that the concrete should have in the fresh state. First of all, it should have a good flowability or filling ability. It should flow easily. It should pass through reinforcement and through narrow openings in the formwork. And thirdly, and very importantly, it should be stable or resistant against segregation. You should not have just the cement paste flowing and the aggregates staying at the place that it was dumped. In order to get this, we need a concrete that is very good in fluidity and also having good cohesion, stickiness, which will avoid segregation of the aggregates. Also, this type of concrete requires new testing methods, and I will show you quickly 4 testing methods that are used for checking self compactability. The first is the slump flow test. The slump flow test is basically done with the conventional slump cone. However, we use a base plate, and when the concrete is poured and lifted, the concrete does not slump but completely flattens, and we have to now measure the final diameter, and also the time taken to reach 50 centimeters is measured. So the mold and base plate are first wetted, the mold is held against the plate, and we fill the concrete without any compaction. The mold is lifted as in the slump test, and we allow the concrete to spread. The time taken for the spread to reach 50 centimeters is noted, and the final spread diameter is also noted. So you will see in this video how the test is done. So here you can see the concrete being poured into the slump, and as we said before, we do not put it in layers or tamp like in the slump test, but without any compaction the slump cone is filled with concrete. After filling, it is topped off, the base plate is cleaned, now what is being indicated is the 50 centimeter diameter. So someone with a stopwatch is going to measure the time taken to reach 50 centimeters about now, and then we allow the concrete to spread and finally take the diameter in 2 orthogonal directions and record that as the spread diameter. So these 2 parameters tell us respectively about the viscosity and also the flowability of the concrete. We want the concrete to flow slowly, that is why the time is important. It should be at least about 2 seconds, and then we have now the spread being measured. This can vary from about 500 millimeters to 750 millimeters depending on the structure and the type of application. The next test is called the V funnel test. So, here basically we have a funnel. So, we have a funnel here which is filled with concrete. The funnel is wetted, filled with concrete, and there is a trap door at the bottom which will be opened to let the concrete flow through. The time taken for the concrete to flow through is measured, and this is usually done by looking from the top and seeing when we can see light through the funnel. Now, this test is also performed after the once again this test is also performed once again after letting the concrete rest in the funnel for about 5 minutes, and this is done to check for segregation. If there was segregation, then the concrete would not flow out easily after having sat in the funnel for 5 minutes, and if we check both the test times, we will see that a concrete with segregation now has a much higher time to flow out than when the test is done immediately. So, let us see how this test is done. So, we have here now the funnel being filled up, and at the bottom of the funnel there is the trap door which will be opened once the concrete fills the funnel. And in this case we are going to see a test where the funnel trap door is opened immediately after filling. This can be now repeated, and we can open the door after letting the concrete sit in the funnel for 5 minutes. If the concrete had a lot of segregation, then you would see a big difference in the two test times. Now, the trap door is being opened, and someone with a stopwatch now sees from the top to see when the concrete has emptied from the funnel. So, we see the surface receding, and we watch until the concrete has flowed through the funnel. And when we see light through the tunnel, then you stop the stopwatch now, and that time is recorded as the V funnel time. Another test which is used now for ensuring that concrete does not get stuck in reinforcement is the J ring test. This is the same as the slump test, or this is the same as the slump flow test, but now a ring made up of reinforcement bars are placed around the slump cone, and when the cone is lifted, the concrete has to pass through the reinforcement and flow along the base plate. The ring as such is made of reinforcement configuration that is as per specifications, or the worst Now, the next test is the J ring test, and here we have the slump flow test repeated with a ring of reinforcement around it. So, when the concrete has to flow, it has to flow through the reinforcement over the base plate. The ring is made such that the reinforcement configuration is as per specifications, or it represents the worst reinforcement density in that application. That is, the type of bars used and the spacing between the bars can represent the worst reinforcement density of the application. Now, we will see how this test is done. So, we have now the base plate, we have the slump cone set, and around the slump cone you see the ring of reinforcement. The cone has been filled and now it is lifted, and you can see the concrete flowing through the bars of the J ring. Now, if this was a bad concrete, not self compactable, you would see aggregates piled up in the center and only paste and water flowing through and reaching the edges, but you see here in the present case we have a good concrete. Now, the spread is measured and compared with the spread that we had from the slump flow without the J ring, the spread should not differ by more than about 5 centimeters or 3 centimeters for us to understand that this concrete would flow through the reinforcement cages without getting blocked. So, this is a test for passing ability of the concrete. The next test is the L box test. This also tells us about the passing ability. It is a more stringent test, however, it is very difficult to do on site, and it is a test that in my opinion is restricted to the laboratory. So, here we have a L shaped box where there is a vertical deposit which is filled with concrete. After the concrete fills up this deposit, there is a trap door that is open, and there is reinforcement here through which the concrete flows, and this horizontal channel has now to be filled with concrete as after it flows through the reinforcement, and depending on whether it levels off in this horizontal channel or not, we say whether it has passed the L box test or not. So, let us see how this test is done. Which one? The ratio of heights at Now, let us see the L box test. This is a test that is also used for looking at passing ability. It is a more stringent test, more difficult to do, and therefore, it is confined more to the laboratories and not done much at the site. So, we have here an L shaped box. We will see now how the test is done, and I will explain the different features of this test. So, here we have the L shaped box. It has a vertical deposit that is being filled now with concrete, and at the bottom there is a trap door, and when this trap door is open, the concrete flows through the reinforcement and it has to fill this horizontal channel. So, you see it is a little bit tricky test. You need a couple of people to ensure that the trap door can be lifted up. Now, the concrete flows through the reinforcement. Again, this reinforcement checks the passing ability, and now the concrete flows into the channel. The height of the concrete at this end and this end are measured, on either end of the horizontal channel are measured, and the ratio should be such that the heights do not vary by more than 20%. That is, the ratio of heights should be more than 0.8. The height should not differ by more than 20%. This is how the measurement of the heights is being done. So, here this is the height at the vertical deposit end before the concrete passes through the rebars, and again the height will be measured here. So, what you see here is the height at the top is being measured. Knowing the depth of the channel, we can subtract the height measured to the surface from the total height, and we can get the height of the concrete. General characteristics of self compacting concrete: we do not use very large aggregates. Generally the aggregate size is limited to 20 or 25 millimeters. There have been cases, however, of self compacting concrete being made with even 40 mm aggregates, but generally we limit the aggregate size to smaller aggregates. This is to facilitate the flow and avoid the risk of segregation. The paste content is about 400 liters per cubic meter. In normal concrete it would be about 300 liters or even less. The water fines ratio is in the order of 0.3 to 0.36, less water because we want to avoid segregation, we want to have a compact microstructure. The fines content is quite high, about 500 to 600 kg per meter cubed of fines are necessary. This is to again give flowability and restrict segregation. So, this means we have a combination of cement, mineral admixtures and fillers, which is much more than normal, reaching about 600 kilograms per meter cubed in some cases. Another aspect that is very different from normal concrete is that the coarse aggregate sand ratio is about 50-50, that is equal to 1. In normal concrete you would have much more coarse aggregate than sand, but in self compacting concrete they are about the same by weight. Additionally, we need a good super plasticizer which ensures the flowability, the fluidity, and lastly in most cases we use a viscosity modifier or a viscosity modifying agent to give more stability, that is resistance to segregation and robustness. Robustness is something very important which we are grappling with in most self compacting concrete applications, which means that we have to get the same concrete in every truck, same self compactability one day to another, and therefore we can have a consistent concrete. A consistent self compacting concrete would be then called a robust self compacting concrete. In India, several projects have used self compacting concrete, including the Bangalore airport, the Delhi metro, the second Vivekananda bridge in Kolkata, the Bandra Worli ceiling bridge in Mumbai, and other applications like liquid gas terminals, one at Cochin, nuclear power plants in Kaiga and Kudankulam, and some buildings like the World 1 Tower in Mumbai have used self compacting concrete. As I said, robustness is a major issue. It is a problem that is limiting the use of self compacting concrete in India. Other problems in India is that we do not have any national standards for self compacting concrete, and lot of cases inadequate testing is done due to lack of know-how or resources. This situation is improving and we will see more and more applications of self compacting concrete in India. We go on to other concretes such as shotcrete or sprayed concrete. This is a concrete or mortar that is placed and compacted by shooting the concrete through a nozzle. It is projected pneumatically at very high velocity onto a surface. So, the concrete hits the surface and sticks onto the surface, hardens fast, and therefore it takes the shape of the surface that it is being projected on. There are two types of shotcrete, dry mix and wet mix. In dry mix the water is added at the nozzle. The more common is the wet mix shotcrete, where all major ingredients are mixed before introduction into the hose, that is, the concrete is mixed as usual, pumped through the hose, compressed air is introduced at the nozzle. This forces the concrete to be projected, and if necessary an accelerator is also added at the nozzle. So this ensures that the concrete is projected fast with high velocity, hits the surface and can also harden very quickly. Shotcrete is used a lot in construction of tunnel linings, slope stabilization and even in repair. The other possibilities are to use shotcrete in sloped and shell roof construction, which is also quite promising. There have been applications of shell roofs being constructed with shotcrete, and this is something that could be used more and more. Fiber reinforced concrete. This is a concrete which has a homogeneous distribution or randomly oriented short fibers. So these fibers are mixed into the concrete as if it was another ingredient such as the aggregate, and the concrete comes out with these fibers mixed uniformly within its body. The fibers used are generally much shorter than the dimensions of the concrete element, and the material of the fiber is stronger and can elongate more than the matrix, that is the hydrated cement paste or the plain concrete. And the fibers are introduced generally in the matrix during the mixing of the concrete. They could be either mixed initially or after the concrete has been mixed, fibers are added and mixed into the concrete. The fibers normally used are steel or polypropylene. Steel fibers will improve the properties of the hardened concrete, especially increase the post cracking strength or toughness. Polymer fibers, polypropylene fibers are added generally to decrease plastic shrinkage cracking that can occur at very early stages of the concrete. I mentioned toughness. How is this toughness measured? This is very important to understand, that fibers do not increase generally the compressive strength or the tensile strength. What they do is they increase the post cracking strength or toughness. The conventional test for flexural toughness is done through the following test. We have a beam with a section of 150 millimeters by 150 millimeters. So cross section is a square of 150 millimeters, and we have a span of 450 millimeters. Loading is applied at the thirds. Now deflection is measured. Deflection has to be measured very carefully. So here it is done with reference to the neutral axis or the middle of the beam. There are two supports placed for a yoke, and on this yoke we have the deflection measuring device such as an extensometer. And if we do this test for a concrete with different dosages of fibers, like we see in this graph, you will get these curves. So these are tests for a 35 megapascal concrete. This is now the load deflection curve that we see. The bottom curve is the concrete without any fibers, that is 0 kilograms. You see the increase in load, peak being reached, and then we have softening. The same concrete with 15 kilograms of steel fibers will have this orange curve. This is for 25 kilograms, 35 kilograms and 45 kilograms. Now you see with 45 kilograms of an adequate steel fiber, we have almost reached this level of the flexural strength of the concrete itself, and we have some sort of a plastic behavior. So this implies that toughness increases, post crack load carrying capacity increases as we introduce fibers into the concrete. There is not a major difference in the peak load itself, that is the flexural strength can increase a little bit, but that is not the reason why we are introducing fibers into the concrete. Where is fiber reinforced concrete used? We use fiber reinforced concrete where we need resistance against shrinkage cracking, local loads coming from compression and impact, especially in floors and pavements. All sorts of pavements we use fiber reinforced concrete. Shotcrete reinforcement can also be with fibers. This increases the post crack load carrying capacity of the shotcrete. Here you see concrete being shot. For a tunnel lining, this is the stabilization of a slope. All sorts of tunnel linings can be done with shotcreting. Here you see the outside of a tunnel. This is say a metro tunnel with shotcreting. Fiber reinforced concrete can also be used for thin elements such as these slabs and curved sections, where you cannot have a reinforcement properly placed because of corrosion potential and so on. We can have distributed fibers replacing the reinforcement and performing the function of the reinforcement. We can expect further applications in structures with fiber reinforced concrete. There is a lot of research going on, lot of development going on, and the promising applications are expected in slender structural elements, where we cannot have a lot of reinforcement, the fibers act as the reinforcement. Wherever we have to limit the crack widths, the elements where crack widths have to be limited due to durability or serviceability requirements, wherever we have to avoid brittle failure, say in shear, when we want to avoid brittle failure and we need more energy dissipation capacity, say in earthquake seismic loading applications, fibers would possibly be used in the near future. In India, fiber reinforced concrete has been used a lot in shotcreting of tunnel linings. This is a very popular application. Lot of projects are being undertaken in the hydroelectric sector and in road projects where we have tunnels, and in cavern projects where underground deposits have to be lined. Shotcreting is used a lot. Fiber reinforced concrete is being used considerably. Fiber reinforced concrete is being used considerably in industrial flooring, where we have to take heavy loads, avoid cracks and a lot of joints, and also in cases where we want something called super flatness, that is very flat floors in precise applications in some industries where we need floors with very good flatness and you cannot have bumpiness or joints coming in. There are, however, no Indian test standards for fiber reinforced concrete. There is a lack of well prepared laboratories and personnel. This is limiting fiber reinforced concrete applications to some extent, but the situation will surely change in the near future. We go on to other concretes such as lightweight concrete. Lightweight concrete is one that has a maximum density of 1900 kilograms per meter cubed, and it is obtained by using low density aggregates. We can also have an intermediate density concrete where part or all of the normal density coarse aggregates are replaced with structural grade low density aggregates, and the concrete now has a density of about 1900 to 2200 kilograms per meter cubed. The low density aggregates which help us get lighter weight in the concrete can be natural. They are expanded by heating or can occur naturally due to the volcanic origin. The expanded aggregates could be made of shale, clay or slate. They could also be processed such as sintered or cold bonded fly ash. There are ultra lightweight concretes or foam concretes with densities of less than 1100 kilogram per meter cube. The strengths are not very high, less than about 7 megapascal. Here the concrete is made with expanded or very low density aggregates such as expanded polystyrene, perlite, blast furnace slag, vermiculite and rubber particles to decrease the density. Or on the other hand, we can have aerated or cellular concrete made with large diameter voids incorporating a foam in the cement paste or mortar. This generates these voids of 0.1 to 1 millimeter, or a foam can be incorporated by some chemical reaction, for example by using fine aluminum powder. Such concretes are used a lot for insulating fills, conduit linings, firewalls and making non-structural panels. In India, lightweight concrete has been used in filling of sunken portions, plinths, utility areas, and also as insulating layers on roofs instead of the traditional brickbat concrete. Some of the applications are given here, say in floor slabs of buildings to decrease the weight, plinth filling and roof insulation. Roller compacted concrete is a concrete which is similar to conventional concrete, but the mix is stiffer and drier, so that it needs very heavy compaction with rollers. Vibratory rollers are generally used, and this is concrete that is laid without any joints. It is laid continuously, and it is such that it can take load very quickly because it is very stiff. With the vibratory compaction, it reaches a consistency which is stiff enough that you can walk on in a couple of hours and even be open to load within a day or so. Sometimes instead of vibratory rollers, we can use a similar concrete in paver machines, especially for making pavements. Such paver machines can be very useful in having pavements prepared very quickly and open to traffic in a few days. So, major applications of roller compacted concrete are in dams and pavements. Up to the year 2013, about 5 dams in India have been made with roller compacted concrete, and we will certainly see more applications in the future. Autoclaved aerated concrete is a lightweight concrete made through the chemical reaction between fine calcareous and siliceous materials. The calcareous component is usually lime combined with or only cement. The siliceous component can be fly ash or ground sand or slag. The cellular nature or the cellular structure is obtained by producing hydrogen bubbles with aluminum powder or by adding a foam or by incorporating air voids. This reaction needs high pressure steam curing. It needs high temperature curing with steam in order to get the reactions going. The final density of the AAC can vary from 200 to 1000 kilogram per meter cube. So, these are very light materials that can be obtained in this process. Applications include blocks, precast structural elements for building construction. There is a lot being done, and this, when it catches on, can lead to other applications. On the other hand, we have high density concrete or heavyweight concrete which has densities greater than 2800 kilogram per meter cube. A typical range would be 3200 to 4200 kilogram per meter cube, and this is concrete that is made with heavy aggregates, high density aggregates such as iron ore or pieces of steel such as punchings, shots and rods. Densities of 3600 to 4000 is obtained usually densities of up to 3600 4000 kilogram per meter cube can be obtained with natural aggregates, both fine and coarse aggregates using hematite, magnetite, limonite and ilmenite. For much higher densities, now we have to go to steel pieces. Steel pieces are cut up and introduced as aggregates to get densities that are even higher. These mixes, that as you can imagine, are generally harsh because we have these heavy aggregates and have also a tendency to segregate. Other than this, the mix proportioning is similar to that of normal concrete. Main application of high density concrete is in nuclear power plants and proton beam therapy clinics for radiation shielding, as the high density of these concrete facilitates the attenuation of gamma and fast neutron radiation. So, this cuts out this type of radiation. When you have moderate or slow neutrons and these have to be attenuated, aggregates containing hydrogen are more desirable, and so boron containing aggregates are useful. In India, HDC has been used in nuclear power plants like in Rawatpata and Kalpakam for radiation shielding. Other applications could include using these concretes as counterweights and to hold down underwater pipeline coverings. Heat resistant and refractory concrete is that which can be exposed to temperatures more than 1000 degrees. Heat resistant concrete is that which can resist up to 1000 degrees, and refractory concrete is concrete that can resist up to 1900 degrees centigrade. These are concretes made with high alumina cement, not the usual Portland cement, but high alumina cement, and this type of cement contains about 40% of alumina and 40% of lime, and the compounds in these cements are mainly calcium aluminates, and the hydration results in calcium aluminate hydrate instead of the CSH forming in conventional concretes. The aggregates used also should resist high temperatures, and materials such as slag are used. Underwater concrete is concrete which has to be very cohesive. It is placed underwater, therefore the cement should not be washed out. It should be able to flow because compaction and pushing the concrete is going to be very difficult. So, the concrete should be cohesive, should flow well, and should self compact underwater. Normally these concretes are made with higher fines content and a viscosity modifying admixture. So, normally these concretes are made with higher fines content and a viscosity modifying admixture to get proper placing underwater. The concrete also should be protected such that the fines are not washed away. So, until the concrete sets, there should not be an effect of the currents or movement of water, and this type of concrete is placed using tremies and pumps, so that the concrete can be taken as close to the floor of the seabed as necessary and placed without the concrete having a possibility of the cement paste being washed away. Polymer modified concrete is where we have polymers combined with Portland cement. This could be styrene, butadiene copolymers or other polymers. This is mixed along with this Portland cement and water to form the binder, and there we have PMC or polymer modified concrete. Here the cement hydration occurs first. After the setting occurs, after the mixture sets and as the water is consumed by hydration, the polymer particles in the voids coalesce, join together into a film that coat the aggregate particles, and the walls of the interstitial voids, that is the gaps and the voids, are coated with a polymer film. This leads to low permeability, better tensile strengths and better bond strengths. So, this is used a lot where you want to increase the impermeability of the existing structure, or we want to provide a coating that has a low permeability, and we want to have good bonding within the polymer modified concrete or to some other material that we are coating that with the PMC. Consequently, applications include flooring screeds, repair, bridge deck and pavement overlays. In India, PMCs are used extensively in waterproofing, repair and strengthening. Flooring applications are also quite common. Recycled aggregate concrete generally refers to that made with aggregates derived from construction demolition waste. We can use concrete, old concrete crushed into aggregate sizes, that is recycled, or the aggregates, the coarse aggregates themselves can be extracted and used in the new concrete, or they could be other materials coming from masonry and so on. Majority of such concretes are used in road subbase construction, engineering fill or landfill construction, and it has a good potential also for use in building blocks, paver blocks and slabs. Other materials that can be also used as aggregates and have been used in other countries are waste glass. This can be used as fine aggregates under some circumstances, and it has been used to get a glittery surface on precast concrete. However, it can be susceptible to alkali silica reactivity, so we have to be careful about the type of glass that is used. Granulated or crumb rubber, pieces of rubber coming from tires has been used to make a low strength flowable concrete. This improves flexibility and the thermal insulation. Bottom ash coming from incinerators have also been used to again make a low strength non-structural concrete. The final special concretes that I wanted to mention is geopolymer concrete, where we have the binder made up of fine aluminosilicates which are activated by alkalis to give polysialates. Sialate is a word that has been coined to represent silicon oxoaluminates. These polysialates are inorganic polymers with chains and rings made up of silicon and aluminum cations in coordination with oxygen. So, chains or rings, just like we would have in organic polymers, are formed in these cases, but with inorganic materials. There are a range of natural materials which can be used, such as zeolite, lateritic rock, soils, clay, mica, feldspar, and waste products such as fly ash and slag. All these can be used in making of geopolymers. Potential applications until now, but this promises a lot, include building, paver blocks, heat and chemical resistant composites, and hazardous waste encapsulation, where these materials, since they are very resistant to heat and chemicals, can be used to encapsulate toxic and hazardous waste. There are many applications which are very promising from geopolymers. These are some of the references. There is an extensive list of references for concrete for all these lectures that we have heard. So, we have had different materials covered. This is the last structural material that we cover in a lot of detail. We go on now to look at non-structural materials, finishes and accessories, and we look at the different accessories. With this we will finish with structural materials, and we will go on to look at materials that are used in finishes, accessories and fittings in the following lectures. Thank you.